Maria G. Mayer and Francis W. Aston were two scientists who had contributed to the study of stability of elements, isotopes, and the mass spectrograph. Maria G. Mayer and Francis W. Aston were two scientists who had contributed to the study of stability of elements, isotopes, and the mass spectrograph. Introduction to Nucleus 2. In this lesson, you will learn to understand the variation of binding energy per nucleon with nucleon number, to understand the existence of isotopes, to understand the working principles of mass spectrometers. The binding energy per nucleon is the binding energy of a nucleus divided by the number of nucleons in the nucleus. The binding energy per nucleon indicates relatively how firmly the nucleons in the nucleus are held together. It is a measure of the stability of a nucleus. Click the steps to see how the binding energy per nucleon of a nitrogen nucleus is calculated. The graph above shows the variation of the binding energy per nucleon with nucleon number A for different nuclides. Each red dot on the graph represents a nuclide. Click the View button to see the name of some nuclides. Note that, except for the lighter nuclides, the binding energy per nucleon is approximately 8 MeV. Nickel-62 has the highest binding energy per nucleon and its value is 8.8 MeV. Which nuclide has the lowest binding energy per nucleon? Answer: Deuterium has the lowest binding energy per nucleon and its value is 1.2 MeV. Nuclides with nucleon number A between 40 and 80 have high binding energy per nucleon. This indicates that nucleons of these nuclides are more firmly bound. Hence, these nuclei are more stable than those having A less than 40 or A greater than 80. Click the Stable Nuclides button. The three peaks shown that helium-4, carbon-12 and oxygen-16 are light nuclides which are unusually stable. How many protons and neutrons does each have? Answer: Helium-4 has 2 protons and 2 neutrons. Carbon-12 has 6 protons and 6 neutrons, while oxygen-16 has 8 protons and 8 neutrons. Light nuclei which are stable normally have equal number of protons and neutrons. Can you suggest some nuclides which have this property? Click the Same Number button for some examples. In nature, there exists both stable and unstable nuclides. Click the Stable Nuclides button to observe the plot of neutron number N and proton number Z for stable nuclides. Click the Unstable Nuclides button to observe the plot of neutron number N and proton number Z for unstable nuclides. Stable nuclides with Z less than or equal to 20 tend to have the same number of protons and neutrons. Click the Z less than or equal to 20 button. For Z greater than 20 or less than 83, stable nuclei contain more neutrons than protons. The ratio N over Z for stable nuclides increases gradually from 1.0 to about 1.6 as the proton number Z increases to 83. Click the Z greater than 20 or less than or equal to 83 button. Nuclides with Z greater than 83 are unstable. Click the Z greater than 83 button. Summary. The binding energy per nucleon is the binding energy of a nucleus divided by the number of nucleons. Nuclides with nucleon numbers between 40 to 80 have high binding energy per nucleon. For stable nuclides, if Z less than or equal to 20, N equals Z. If Z greater than 20 or less than or equal to 83, the ratio N over Z for stable nuclides increases gradually from 1.0 to about 1.6 as Z increases to 83. Nuclides with Z greater than 83 are unstable. Elements are identified by their proton numbers. Nuclides with the same number of protons but with different number of neutrons are called isotopes of an element. Naturally occurring elements usually are mixtures of isotopes. The atomic mass of an element given in the periodic table is the average mass of all isotopes of the element. Click the carbon button to see the atomic mass of carbon. Click the next button to see the isotopes of carbon. The table above shows 15 isotopes of carbon. The nucleus in the most common isotope of carbon has 6 protons and 6 neutrons. Only 2 isotopes of carbon are stable. The rest are unstable and radioactive. All isotopes of an element have the same chemical properties since they have same number of electrons. They therefore fit into the same box in the periodic table of the elements. Whilst the chemical properties are the same, the nuclear properties of isotopes are different. The chart above shows isotopes of some elements. Notice that some of the isotopes are stable, whilst many are unstable and radioactive. Isotopes occur naturally or can be artificially produced in nuclear reactions. Referring to the chart, how many isotopes does oxygen have and how many of them are stable? Answer: there are 12 isotopes of oxygen and 3 of them are stable. Summary. Nuclides with the same number of protons but with different number of neutrons are called isotopes of an element. All isotopes of an element have the same chemical properties but different physical and nuclear properties. Isotopes can be stable or unstable and radioactive. Isotopes can be naturally occurring or artificial. Since its invention about 100 years ago, mass spectrometry has become an essential tool used by many scientific and medical researchers. Mass spectrometers are used to identify the type of atoms. Today, many different types of mass spectrometer are in use. In this activity, we shall study the working principles of the Bainbridge mass spectrometer. The mass spectrometer is used to determine the masses and relative abundance of the different isotopes of an element. The main components of the mass spectrometer are the ionizing chamber, accelerator, velocity selector, deflection chamber, and detector. Click the Label button. We will now look at the function of each component of the Bainbridge mass spectrometer. The sample is first vaporized by heating and then enters the ionization chamber S. Click the ionizing chamber button. The electrically heated metal coil emits electrons which are attracted to a positively charged plate called the electron trap. Collisions between the electrons and atoms of the vaporized sample produce positive ions. These positive ions are pushed out by the positively charged ion repeller. The positive ions are then accelerated, pass through 3 slits and emerge as a collimated beam. Click the accelerator button. Ions with different velocities enter the velocity selector. Click the velocity selector button. In the velocity selector, all the positive ions experience an upward electric force and a downward magnetic force. For ions with a certain velocity, the two forces are equal in magnitude. These ions move undeflected through the velocity selector and emerge from the slit S2. When these ions enter the deflector, they experience a magnetic force that causes them to move in semicircular paths. The radius of the path of an ion depends on its mass and charge. Since all the ions have the same charge, lighter ions are deflected more than heavier ones. Click the deflection chamber button. The detector can be a piece of photographic plate. Ions with different masses strike the photographic plate at different points. Click the detector button. The mass-to-charge ratio of an ion can be determined by noting the values of the electric field E, the magnetic fields B and B', and measuring the radius of the path of the ion. The ions that leave the velocity selector have the same velocity v. Click the expression for v button. An ion of mass m and charge q in the magnetic field B' of the deflection chamber experiences a magnetic force which causes it to move in a circular path of radius r. Click the expression for mass to charge button. Ions of two isotopes of uranium, uranium-235 and uranium-238, move with a speed of 1.15 times 10 to the power of 5 meters per second in the deflection chamber of a Bainbridge mass spectrometer. The ions are all singly ionized and the magnetic flux density is 0.750 Tesla. What is the distance d between the two marks on the photographic plate? Click each step to see the solution. Notice that the mass spectrometer is able to convert the small difference in mass into an easily measurable distance of separation. What happens to the radius of the path of each ion if the magnetic field is increased? Answer: with a stronger magnetic field, the radius of the path of each ion decreases. A strong magnetic force acts on the ion, causing a greater deflection. Summary: in the Bainbridge mass spectrometer, the mass-to-charge ratio of an ion is given by m/q equals b prime r over E.